So, let's go through the announcements. Oh, that's past due. Just check. Yeah. Well, don't need that line. The first chapter 2 homework is due on the 18th. That's Wednesday this week. The second chapter 2 homework is due on Monday the 23rd. That's Monday next week. There is a lab on Wednesday on the 18th. So we will have a lab this week. I just set up an announcement on Blackboard to remind you. On Monday, the 23rd, in the SI session, you'll have a review of chapters 1 and 2. The chapter 2 quiz will also be on Monday in the SI session. And then the exam on chapters 1 and 2 will be on Wednesday. The exams, along with the quizzes, they got more questions. They're worth more. Yes.
On the quiz alone, how much do they affect the overall grade?
So let's see, how do they quizzes and exams are about 60% of your grade. And then the quizzes, let me just check. Check the numbers real quick. So quizzes and exams are about 60% of your grade. The quizzes are 25 points and the exams. So each quiz is worth, so the quizzes are 25 points. The exams are 150 points each, and there's about 2 to 3 quizzes per exam. So they make up about a quarter of the 60%, the quizzes. A little bit more than that, right? Yeah. The exams are worth more than the quizzes. Yes. Quiz next Monday. Exam next Wednesday. This is all on the schedule. And so if you look at the schedule, chapter 2 quiz, exam. And it will be an SI. And the exams have got more questions than the quizzes. We've got, yeah. So we were talking about acceleration. The general equation for acceleration is that acceleration is the rate of change of velocity. So acceleration is final velocity minus initial velocity over time. So you can rewrite that as final velocity is initial velocity plus acceleration times time. And you can also solve it for, initial velocity is final velocity minus acceleration times time, and time is final velocity minus initial velocity over acceleration. So in general, this is very common if you're trying to find your final velocity. It's a useful equation. And one of the cases of constant acceleration that's common is gravity, where you have a constant downward acceleration of 9.8 meters per second squared. And for a falling object, so distance for, for drop thing is 1/2 g squared. This is a general case of the distance for any object that starts from rest. Distance would be 1/2 acceleration times time squared. But if it's a falling object, we use gravity. The only problems I'll have where I'm asking you for distance will involve gravity. So, and the velocity is proportional to the time. So for, in that case, final velocity is just going to be g times t, because your initial velocity is 0. And so it's just this equation with 0 in for initial velocity. Because when you drop something, your initial velocity is 0, you think of your initial position as 0. And so distance is proportional to time squared. It's a parabola. Velocity is a straight line. If you look at this, the slope of this line as it curves up corresponds to the height of this line. That's the relationship. Because velocity is the rate of change of distance. Now, acceleration due to gravity, it's always happening. So if you throw something up in the air like this, when it comes back to your hand, it turns out it will be accelerated down all the way up, slowing down, and then it'll speed back up on the way back down. And it turns out that process is symmetric. It'll slow down the same, it'll speed up the same amount on the way down that it slowed down on the way up. Which means if you throw something up in the air, and when it comes back to your hand, it'll be going at the same speed that you threw it up. Yes. That's the acceleration. That's the rate of change of velocity. So this starts with a velocity that's positive, we're pointing up. And it gets smaller and smaller because every second it reduces by 9.8 meters per second squared until it comes to a stop at the top. And then it starts getting bigger and bigger downwards. So you can think of it going from positive to negative. And when it gets here, its speed on the way up, how fast it was going up will be the same as how fast it's going down, but the sign will. And that's basically because it takes the same amount of time to go up as it does to go down. So you start with some velocity, you come to a stop, and then you speed back up. That make sense? Okay. So it's always being accelerated downwards, but it started with a starting upwards velocity, which eventually becomes a downwards velocity of the same size. And it turns out actually it'll have the same velocity speed, same speed, same size of velocity at every height. So at this height, they're the same, at this height, they're the same. So here we have a dropped penny. We drop a penny and it falls a distance of 490 meters because apparently we found somewhere very high up to drop a penny from. I think that's taller than the tallest building in the world. So, Actually, that might be close. The Burj Khalifa is like stupid tall. But you couldn't successfully drop a penny out. No. Yeah, this is a physics problem. I chose that number because it gives you a nice answer, not because it's realistic. In reality, the penny would slow down due to air resistance, so which we're not going to worry about. So a drop penny, it falls a distance of 490 meters. The question is, how much time does it take to fall? Name? So we're looking at distance. We know the distance. Distance is 1/2 gt squared. What we can do is we can solve this equation here for time. So distance, 2 times distance is g2 squared. 2 times distance over t. Over g is t squared. So t is the square root of 2 times distance over g. And the question is, how long does it fall? Like the distance it falls, and then how fast is it traveling when it hits the ground? So, I mean, the time it takes to fall, how long does it fall? That's asking for time. This is not distance, it's time. So this is time. And then how fast it's traveling when it hits the ground is velocity. So for the first one, you're going to use these equations. For the second part, you're going to use this equation. And g is 9.8 meters per second squared. So the first part, distance will be 1/2 g2 squared. So this is so if we solve that for time, 2d equals g2 squared, 2d over g equals time squared. Time is the square root of 2g over g. So now we can plug in our distance and g. So 2 times 490 meters divided by 9.8 meters per second squared. Because the distance we fell divided by our acceleration g times 2. That's 100. It's 10 seconds. And to figure out how fast it's going after 10 seconds, well, velocity, or final velocity is initial velocity plus acceleration times time. Our initial velocity is 0, our acceleration is g. Because it's dropped, it started from rest, so it didn't have any speed when it started. And it's just feeling gravity. So our velocity is just going to be g times t, 9.8 meters per second squared, times 10 seconds. One of the seconds cancels, and we get 98 meters per second. Any questions? Yeah, really just plugging in numbers here. And when you have a drop thing, your initial velocity is always 0 and your acceleration is always g. So everybody got this? Okay, let me.
Now, wouldn't you say that you're not dropping something to accelerate? But what do you like people where?
Yeah, we used that in that last problem.
What would you use this on?
So this is actually asking about velocity. So distance isn't involved. And this isn't something starting from rest. So this is, we have a boat. We know its acceleration. We know it took 30 seconds to come to a stop. So we know the final velocity. We're trying to find the initial velocity. So because we know the acceleration and the time, and it comes to a stop, that tells us our final velocity is 0. We want to figure out what we're looking for is the initial velocity. For that, you're going to use velocity and acceleration equation. You can use the one that was solved for initial velocity. It's did you say 45 meters per second? No, it is not negative. Because notice how you're subtracting acceleration times time here, with a minus sign on the acceleration and the minus sign here end up canceling. So final velocity is initial velocity plus acceleration times time. So if you solve for initial velocity is final velocity minus acceleration times time. So if we plug in our numbers, initial velocity is our final velocity of 0 minus negative 1.5 meters per second squared times 30 seconds. We lost a total of 45 meters per second in speed. So that means our initial velocity where we started was at 45 meters per second. Because we have minus a negative. So because it's 30 seconds minus one, at 1.5 meters per second squared gives you 45. You can figure this out in your head, yes, it's possible. But that's the like. You also need to make sure you get the signs right, so it helps to write it down on paper. So here, if a ball is fired upwards at 49 meters per second from the ground, how long does it take to reach its maximum height when it has zero velocity? And here, your acceleration, this is easiest to calculate if you assume that your acceleration is negative 9.8 meters per second squared. Your initial velocity is 49 meters per second, your final velocity is 0. So, starting with final velocity is initial velocity plus acceleration times time. Final velocity minus initial velocity is acceleration times time. So time is final velocity minus initial velocity over acceleration. And we plug in our numbers. Our acceleration is negative 9.8 meters per second squared because it's down. Our initial velocity is positive 49 meters per second, and our final velocity is 0 meters per second. So time is 0 meters per second minus 49 meters per second divided by 9.8 meters per second squared. Those minus signs will cancel, and you'll get 5 seconds. And it's easy to make a sign error here and get negative 5 seconds. And that's a sign that you made a mistake somewhere. Because shouldn't take negative time to go for something to try. Everybody got this? Okay. So that was acceleration in a straight line. We can also talk about acceleration in a circle. So if you have an object that's traveling in a circle, like so, I'm trying not to hit myself in the head. So this has a constant speed. It's traveling at the same speed the whole time, but its direction is constantly changing. And that means it's accelerating. In this case, the acceleration is being caused by the string. So if you have an object that's in uniform circular motion at a constant speed, it'll be constantly changing directions. And therefore its velocity will be constantly changing directions, and therefore it's constantly accelerating. Since there's a change in direction, there's a change in acceleration. And so for circular motion, you guys okay with me erasing this here? Yeah. So for circular motion, when you're traveling in a circle, that acceleration is always towards the center of the circle. It's at right angles to the direction of motion. And it points towards the center of the circle. So as this travels around my head, its velocity is constantly changing direction, and the acceleration is towards the center of the circle along the road. So if I draw a circle, I'm traveling at some velocity. Draw this a little better. Have some velocity that I'm traveling at. My acceleration will be towards the center of the circle, like that. And it turns out, and this is what's known as centripetal or centripetal acceleration, or you can think of it as circular acceleration. AC, A sub C. And it depends on the size of the circle and how fast you're going. So for example, in a car going around a corner, this is centripetal or center-seeking acceleration. In a car going around a corner, this acceleration is provided by the tires of the car, by friction from the tires of the car. And the car will remain in a circular path as long as there's enough friction to keep the car, to provide the appropriate acceleration. And if there's not, well, you get understeer. And if there's not, in a controlled, fancy way, you get drifting. But when you go around the corner, the acceleration is being provided by the friction between the tires and the road. And it's towards the center of the corner, towards the center of the curve. And the formula for centripetal acceleration. So centripetal acceleration is the speed squared, or the velocity squared, divided by the radius of the circle. So the faster you're going, the bigger the acceleration is, and the tighter the circle is, the bigger the acceleration is. So any object moving in a circle with radius r and speed v. So that's just the speed. When you square the velocity, it gets rid of the direction, so you don't have to worry about the direction. So speed squared over radius. it increases as the square of the speed. So if you double your speed, you quadruple the necessary acceleration. And as the radius decreases, the centripetal acceleration increases. So for the same speed, with a long rope, I don't need as much centripetal acceleration for the same speed as I would with a smaller one. And that's how fast it's moving around the circle. So the reason the speed gets basically squared is because you're both moving faster and you're going around the circle in less time because you're moving faster, kind of thing. But speed gets squared divided by the radius. So a smaller radius requires a bigger acceleration. It's harder to make a tight turn than to make a big turn. So if you want to find the centripetal acceleration of a car going at 12 meters per second on a circular track with a radius of 50 meters, we can go through and do the calculations for that. So we know our speed is 12 meters per second. Our radius is 50 meters. So our centripetal acceleration is velocity squared over radius, which is 12 squared over 50 meters. That's 144 divided by 50, which comes out to two significant figures, 2.9 meters per second squared. 2.88 exactly, and then it needs to be rounded. So there it is worked out. It's 144 meters squared per second squared over 50 meters. The meters cancel. We get 2.88 meters per second squared. But we need to round to 2.9 meters per second squared because two significant figures. What? That's the distance around a circle based on the radius. This, we're talking about the acceleration to travel in a circle, is centripetal acceleration or circular acceleration is speed squared over radius. So the previous class we were dealing with, we were talking about how much time it took to go around a circle. 2 pi r tells you the circumference of the circle, the distance around the circle as a function of the radius. But this is finding the acceleration required to go around a circle at a certain speed. So here we're at. So we have the speed here. If we wanted to find the speed here, for example, we would use 2 pi times the radius and then the time it takes to find the speed. So here we want to compute the centripetal acceleration in meters per second squared of the Earth in its nearly circular orbit around the sun. Well, the radius is 1.5 times 10 to the minus 11 meters. That's 150 million kilometers. The speed is 3.0 times 10 to the 4 meters per second. That's 30,000 meters per second. So if we plug those numbers in, 3 times 10 to the 4 meters per second, when you square it, the 3 gets squared to 9, the 10 to the 4 gets squared to 10 to the 8. Because when you square 10 to the 4, you just multiply the 4 by 2. So you get 9 times 10 to the 8 meters squared per second squared, divided by the radius, which is 1.5 times 10 to the 11 meters. And that comes out to 6 times 10 to the minus 3 meters per second squared. Not a huge acceleration. And that sort of makes sense because it's provided by gravity from the sun. And we're a long way away from the sun. The gravity from the sun is not very strong. So this is 0.006 meters per second squared. Like less than 1,000 of the gravity from Earth. So here, let's say you have a child on a 10-meter diameter. Note that that is a diameter. Merry-go-round traveling at 1.5 meters per second. So this is a merry-go-round. It's 10 meters in diameter. The kid's on the edge of it, traveling at 1.5 meters per second. So what is the centripetal acceleration of the child? Remember, diameter is twice radius. The diameter is all the way across the circle, while radius is from the center to the edge. So, because radius is half the diameter, the radius is 5 meters. So let's plug our numbers in. Acceleration is speed squared over radius. So radius is diameter divided by 2. So 10 meters divided by 2, it's 5 meters. Acceleration is going to be 1.5 meters per second squared divided by 5 meters, which comes out to 0.45 meters per second squared. Sorry, 0.450. So here, we have a mass that's spun on a string. It's accelerating at 200 meters per second squared, and it's moving at a speed of 5 meters per second. So the question is, how long is the string? So for this, we try to find radius, acceleration and speed. So radius times acceleration is speed squared. So radius will be speed squared over centripetal acceleration. And if we wanted to find speed, speed is going to be the square root of radius times centripetal acceleration. Yes, it is 0.125 meters. So centripetal acceleration is speed squared over radius. So radius is speed squared over centripetal acceleration. So 5 meters per second squared over 200 meters per second squared. Gives us a radius of 0.125 meters. So this is 25 divided by 200, which is 0.125. When you Oh, yeah, then you didn't finish it. So, so here, this is what you do if you're trying to find the velocity. Multiply both sides by radius, velocity squared ends up being speed squared equals centripetal acceleration times radius, so speed is the square root of centripetal acceleration times radius. So here, if a vehicle has a centripetal acceleration of 160 meters per second squared and is traveling at in a 20-meter diameter circle, what is its speed? Remember, diameter is twice radius. Yeah, also on tests and quizzes, you'll have calculators, so you can always take the square root. So this, we're looking for its speed, velocity. So you solve for velocity squared and then take the square root of both sides. So yes, it is 40 meters per second. So centripetal acceleration is speed squared over radius. So centripetal acceleration times radius is speed squared. So speed is square root of a centripetal acceleration times radius. Our radius is half the diameter. This is a 20-meter diameter circle. So the radius is 10 meters. So our velocity is going to be the square root of 160 meters per second squared times 10 meters, which will be square root of 1600 meters squared per second squared, which is 40 meters per second. Everybody get? Yeah.
So, I know that you wrote down like the list of formulas on the side of it. Are we using all of this?
So you mean these?
Yeah, those.
These are all the same equation. I just solved for each different variable.
Oh, okay.
So like the general idea is that if you don't want to solve it, you can just write down like this one, and this one, and know all the three ways you'd solve it.
Oh, okay.
So, but these are all the same equation. I've just done some algebra.
Okay, because when you wrote that down, I'm just confused, like, which.
And the
one was I
same
using?
here, these are all the same equation. I just solved for each different variable.
That'll make sense.
That's just because it helps some people who have trouble with doing algebra on the spot, because then they can do it in advance and just have it in advance on their formula sheet.
Oh,
I mean, if that helps you, use it. Um, but yeah, so these are all the same equations, okay, as well, so. So here's another one. Here is one where you're gonna have to use the fact that the circumference of a circle is 2 pi times the radius to figure out the velocity. You want to figure out the speed. So Lund is the moon of Mungor, because I'm reusing names. It orbits at a distance of 2 times 10 to the 5th kilometers. That's 200,000 kilometers, and it completes an orbit every 10 hours. One is booking it. This is probably actually wrong for the gravity we calculated for Mungor before, but let's not worry about it. So what is the centripetal acceleration of Lund? So for this, centripetal acceleration is speed squared over radius, but you're going to have to find the speed. So remember, your speed is just going to be distance over time. And your distance is going to be the circumference, which is 2 pi times the radius, and the time is the 10 hours here, which we'll need to convert to seconds. So 1 hour is 3,600 seconds. That comes from that there's 60 seconds in a minute and 60 minutes in a minute. So centripetal acceleration is speed squared over radius. You need to know the speed. Our radius, 2 times 10 to the 5th kilometers, or 2 times 10 to the 8th meters. So we need to convert that to meters. We just multiply by 1,000. We go from kilometers to meters. And our speed is the circumference over the period. 2 pi times the radius over the time it takes to orbit. So 2 pi times 2 times 10 to the 8th meters divided by 10 hours. So that's 1.2566 times 10 to the 9 meters divided by 36,000 seconds. Because 10 hours is 10 times 3,600 seconds, which gives us 3.49 times 10 to the 4th meters per second. Then our acceleration is 3.49 times 10 to the 4th meters per second, quantity squared, divided by 2 times 10 to the 8th meters. And that will come out to 6.09 meters per second squared. Yeah, no, that's reasonable. It's just Moon is much closer to Mungor than our moon is to Earth. Hence why it orbits so fast. So we're using 2 pi r to find the distance. So, this is going around once every 10 hours. We want to figure out how fast it's going. So to find out the distance it travels once is the 2 pi r. And then we're dividing by the 10 hours. So our velocity is going to be 2 pi r over the period. So here we have a 1 meter diameter flywheel that will break, it'll tear itself apart if the centripetal acceleration of the rim is greater than 8 times 10 to the 6th meters per second squared. So if it's going to have a centripetal acceleration bigger than that, this flywheel will fail, probably violently. So what is the maximum speed that the rim of the flywheel can reach? So here, we're looking for the speed. We know the acceleration. We know the diameter is 1 meter. We know the centripetal acceleration. We're looking for the speed. So this, we're going to end up using that speed equals square root of radius times acceleration. Centripetal acceleration is speed squared over radius. So speed is square root of centripetal acceleration times radius. And our radius is 0.5 meter. because our diameter is 1 meter, so our radius is half a meter. And so our velocity is going to be 8 times 10 to the 6 meters per second squared times 0.5 meters, which will give us 4 times 10 to the 6 meters per second squared, which the square root of that is 2 times 10 to the 3. Meters squared per second squared. 4 times 10 to the 6 meters squared per second squared, which is going to be 2 times 10 to the 3 meters per second. Okay, here we have a car traveling at 36 kilometers per hour. It has a centripetal acceleration of 10 meters per second squared. What is its turning radius? So what's the radius here? So remember, 1 meter per second is 3.6 kilometers per hour. So we will have to do a conversion, and then we're going to plug in for the radius. Formula we'll end up using is radius is speed squared over acceleration. Our first step will be to find the speed in meters per second. So 36 kilometers per hour times 1,000 meters per kilometer times 1 hour per 3,600 seconds gives us 10 meters per second. I do choose the numbers for these example problems to be pretty. So 10 meters per second squared over a radius over acceleration of 10 meters per second squared. That's 100 divided by 10. Our radius is 10 meters. And that is all for today. I'm gonna have to update those announcements. So yeah. So that was all for circular motion. We'll have some final bits for the chapter on Wednesday, finishing it off. I'm gonna end the meeting as long as nobody has any questions. Oh, one last announcement. The tests are graded. Your quizzes are graded. The grades are up on Blackboard. I didn't hand them back today because there's still a few people who need to make up the quiz. But if you want to see the quiz, you can come to my office and I'll happily show it to you and go over it with you. So I'm going to